Question 1. This question is about compounds that contain fluorine. Sodium fluoride contains Na plus sodium ions, and fluoride ions F minus. Na plus and F minus have the same electron configuration. So therefore they're isoelectronic. Don't really need to know that, but it just means same electron configuration. Explain why fluoride ion is larger than a sodium ion. Well, a fluoride ion and Na plus. There's Na plus, there's fluoride. A fluoride ion is going to have fewer protons. Fluoride ion has, actually it's better if I just type it in. Fluoride ion has fewer protons, hence a lower nuclear charge. And what does this mean? It's got fewer protons, hence a lower nuclear charge. Weaker attraction between nucleus and outer electrons, hence fluoride ion is larger than a sodium ion. Because remember, if it's larger, it's going to have more shielding, therefore it's going to be a weaker attraction, it's going to have more electron shells, weaker attraction between nucleus and outer electrons, as fluoride ion has fewer protons, aka a lower nuclear charge, and weaker attraction between nucleus and outer electrons. 1.2. Explain in terms of structure and bonding why multiple of sodium fluoride is high. We're just going to talk about the ions, right? So we're going to say electrostatic forces of attraction between oppositely charged ions, and I would actually include the ions, so in this case Na plus and F minus, because the oppositely this whole bit, electrostatic force of attraction between oppositely charged ions, you could apply this to any question where it's about that. However, this, the Na plus and F minus, is applying it to this question because that's what sodium fluoride has. And a lot of the times, the mark scheme wants you to just apply it to the question, not just copy and paste A1. So it's better to be safe and just write NaF and S minus. So the electrostatic force of attraction between oppositely charged ions, NaF and S minus. This means lots of energy needed to overcome the forces / break the forces. And that is the end of question 1.2. Electrostatic force of attraction between oppositely charged ions, Na plus and F minus. Lots of energy needed to overcome the forces. 1.3. The ion H2F plus is formed when hydrogen fluoride gains a proton as shown in the equation. Name the type of bond formed. It's going to be dative. Like I said, anytime it usually says name type of bond formed, and you can clearly see it's bonding topic. It's usually always dative, coordinate bond, or coordinate bond. Explanation, well, because a lone pair of electrons is donated from F. A lone pair of electrons is donated from F. And let's just say coordinate bond here. Then 1.4 and 1.5. 1.4, draw the shapes of the SbF6 minus ion and the shape of the H2F plus ion. Because it's got a minus charge and a plus charge, we're going to have square brackets, right? The minus out here, and we're going to have Sb in the middle. We're going to have F. Obviously it should be all inside the brackets. F and then F here and F here. The name of the shape, so 1, 2, 3, 4, 5, 6 Fs. Name a shape. It is not square planar. That's like XCF4. This is SBF6. This is octahedral. Octahedral. Then H2F plus, because we've got a positive, we've got a charge, square brackets, put positive charge, and you learn these things the more you go through these past papers. So the H2F, so we've got fluorine. It's not a linear shape. We're bonding to two hydrogens. Now, how many lone pairs of electrons is this going to have? Because this is going to have none. We already bonded to 6. And what is SB in? Well, SB is in group. Can't really see. SB is in group antimony. Group 5, right? It's attached to 1, 2, 3, 4, 5, 6. And then the minus charge. So yeah, it's going to have no lone pairs of electrons. H2F, while fluorine is in group 7, it's attached to 2 hydrogens, right? So clearly by that logic, well, 7 minus 2 is equal to 5, so it's going to have 5 pairs of electrons. However, it has a plus charge, and if it's got a plus charge, therefore we're going to subtract an electrons, therefore it's going to have 4 electrons, so it's going to be 2 lone pairs of electrons. And what is this called? Well, this is called bent. It's literally called that, bent shape. It's just like H2O, right? H2O. And for these type of questions, you need to memorize similar kind of compounds to it, and then maybe write them all down and then compare it and then see, okay, H2F, that's like H2O, right? H2O is bent, it has 2 lone pairs of electrons, etc, etc. It has a lone pair of electrons, but in this case we're going to have 2 lone pairs. And at 1.5, hydrogen fluoride reacts with ethine, C2H2 as shown in the equation. All compounds in the gaseous state. Delta H is minus 179. Uses data table 1 to calculate value for bond enthalpy of a CF bond in the product. Well, we know delta H, in this case, mean bond enthalpy, energy. I'm not going to write the whole thing. Energy required to break bonds, so energy bonds minus energy. Actually, I'll say energy bonds broken. Energy required to break bonds minus energy bonds formed. We know delta H is minus 179, so let's substitute that in. Minus 179 equals. They really like to ask these type of questions with mean bond enthalpy data, and they are slightly tricky. I've seen one in A-level paper which is obviously slightly harder, but generally, yeah, you need to know this equation off by heart first. Then you can even approach this question. So we want to find a value for the bond enthalpy of a CF bond in the product. So we want to find this CF bond. Now, energy required to break bonds, this. So let's find this out. So we got CH, so 412, plus we've got C11C, that's 837, plus we've got another CH, so plus 412. And before I even do, minus energy bonds formed, I'm just going to simplify that, just so I don't make any errors, because there's going to be a lot of numbers. So 412 plus 837 plus 412, 1661. 1661, and obviously I almost forgot the 2HF. But what does that mean? Well, that means all we're going to do is just put brackets around it. And now what does that mean? Well, that means HF, which is 562, 2 times by 562, right? Just put brackets around it, makes a lot more sense. And that's all we're going to do. So it's going to be plus 2 times by 562 minus 179 equals 1661 plus Actually, I'm just going to do 2 times 562, 1124, 1124 plus 1661, 2785. Minus energy released from bonds are formed. Well, we've got 1 CH, 2 CH, 3 CH, so 412. 412 times by 3 plus, we've got a carbon-carbon bond, 348, 348 plus, well, we've got a carbon-hydrogen bond, another 412, and then we've got 2 carbon F bonds, which we were trying to find, so plus 2y. 2x, we'll just say 2y. So minus 179 equals 2785. Now let's put these numbers in a calculator. 412 times by 3 plus 348 plus 412, 1996 plus 2y. 2785 minus 1996, 789. Minus 179 equals 789 plus 2y. Minus 179 minus 789. 2y equals minus 968. Y equals minus 968 divided by 2 minus 4. Actually, I think I did a mistake here somewhere. Minus 179 equals 2785 minus 1996 plus 2CF. So plus 2y. So 2785 minus 1996 will give me 789 plus 2y equals that. Oh, because of this minus, this is not going to be plus 2y, it's going to be minus 2y. So then we get that minus 2y. Therefore we get 2y equals 789 plus 179, which is 968. And therefore we get 968 divided by 2, 484 is the CF bond enthalpy. And the reason we divide by 2 is because we're trying to find the bond enthalpy of a single CF bond. There are 2, but we don't want 2, we just want 1. It's going to be 484 kilojoules per mole per minus 1. That is the end of question 1.